somewhere under the Arctic ice, in water a hair above freezing, a shark is swimming that may have been alive before the first steam engine was ever built. Not a fossil, not a legend. A living animal, the Greenland shark, and the best evidence we have says this species can live for something close to 400 years. It is the longest-lived backboned animal we have ever found. And here is the strange part. It manages this while growing less than a centimetre a year, often in near total darkness, its eyes so clouded by a parasite that for years scientists assumed it could barely see at all. So the question that matters isn't how old it is, it's how anything survives that long down there at all. By the standards of most large predators, almost everything about this animal seems impossibly slow. It is cold to the core. It lives where the light never really comes, and food can be hard to find. And yet no other vertebrate we have ever aged appears to live longer. Two mysteries sit underneath that. First, how could anyone measure centuries of age in an animal with no rings to count? And second, harder still, even if the number is right, what kind of body can simply keep working for that long? The first answer turned out to be hidden inside its eye. The second is only now beginning to come into focus, and the answer may involve far more than cold water. None of it needs to be exaggerated. The plain facts are enough. Start with the claim, because it sounds impossible, and it very nearly is. An adult Greenland shark alive in the Arctic right now could have been born centuries ago, long before most of the machines and maps we take for granted existed. That is not a storyteller's flourish. It comes from a study that carbon dated the eye lenses of 28 of these sharks, all of them females caught as fishing bycatch. Reading those lenses, the researchers concluded that this species' maximum lifespan is at least 272 years, and that the single largest shark they examined was somewhere around 392 years old. That top figure carries a wide margin, give or take, roughly 120 years, because it's a scientific estimate with a genuine range, not a number stamped on a birth certificate. But even the lower end of that estimate makes it the longest-lived vertebrate currently known. That single result reset the record books. Not for the oldest thing alive, there are clams and deep sea sponges that outlast even this, but for the oldest backboned animal we have ever found. The longest-lived vertebrate on Earth is not a giant tortoise sunning itself on an island. It's a cold, gray, slow-moving shark almost nobody ever sees. And the moment you accept that number, it drags two harder questions in behind it. The first is simple suspicion. How could anyone possibly know? You can't ask a shark its age, and unlike a tree or a clam, it doesn't lay down neat annual rings you can count. For most of the last century, the honest answer was that nobody knew people guessed, and guessed low. The second question is bigger. Set aside how we measured it. How does an animal physically keep going for that long? Cells wear out. Bodies break down. 400 years is deep time for a living thing. Some combination of where this shark lives, how slowly its body runs, and its underlying biology appears to be slowing that decline to a crawl, and to understand it, you have to start not with its age, but with the water it lives in. The Greenland shark lives in the cold. It's tied less to a particular depth than to cold water, generally between roughly -1 and 10 degrees Celsius. To stay in it, it goes deep, turning up anywhere from near the surface in the far north down to around 2,200 meters, well over a mile down. That preference is so strong, it tells you where to find the animal. In the far north, cold water sits close to the surface, and a Greenland shark can hover just under the ice. Farther south, it follows the same cold downward into the frigid deep layers, while the sunlit water far above turns warm which is how an Arctic species has even turned up beneath the warm surface of the Gulf of Mexico. It isn't tied to one patch of ocean. It's tied to a temperature. Everything about the animal matches that setting. It is big and heavy and unhurried, one of the slowest swimming sharks of its size ever measured, cruising the black water at a pace a person could easily outwalk. They can exceed 5 meters in length and weigh over a ton, with the largest historical estimates approaching 7, though most are smaller, between 2 and 4 meters. It is built like an animal that is in no rush to be anywhere, because it isn't. And then there's the number that quietly points at extreme age. By the best estimates, it grows less than a centimeter a year. Less than a centimeter. At that rate, a shark may add barely the width of a fingernail in a full year 1 tagged individual grew only about 8 centimeters across 16 years. Think about what that implies. To reach 4 meters at that pace, an animal has to keep growing, steadily, for a very long time. Size became a rough clock, good enough to suggest these sharks were extraordinarily old, though not precise enough, on its own, to prove it. And the slowness isn't laziness, it's chemistry. Near freezing water lowers many of the metabolic demands on a cold-blooded animal, reducing how much energy its body needs just to keep running, and researchers have actually measured exceptionally low energy demands in these sharks. Here is the link they keep coming back to. A body running that slowly may also wear out that slowly, its low energy demand stretching its whole life out. It's a reasonable idea, well supported by those measurements, but the direct step from a slow metabolism to a 400-year lifespan is still a hypothesis, not a proven mechanism. Cold and low energy demand are probably part of the foundation, but, as newer genetic work is starting to show, they are not the whole structure. So we have a plausible picture. A giant, slow animal, growing at a crawl, in water that keeps its whole body idling. That gives researchers their first real clue, but not, on its own, a complete explanation. It doesn't prove that any particular shark is. Slow growth is suggestive, not conclusive. So, how did anyone actually pin real numbers, a maximum past 270, a largest specimen near 400, onto an animal with no rings to count? The answer is one of the more ingenious things in modern marine science, and it hides in the last place you'd look on a shark: its eye. Here's the problem scientists faced. To age most fish, you look at hard tissues, ear bones, spines, vertebrae that build up layers over time, like rings. Greenland sharks don't give you that. Their bodies are soft, their skeletons are cartilage, and there's no reliable clock in the usual places. A shark's skeleton isn't bone at all. It's the same flexible material as the tip of your nose. And it simply doesn't record the years the way a tree trunk or a clamshell does. So for decades, the animal's true age stayed an open guess, and, tellingly, almost everyone guessed too low. Combine that with how rarely anyone encounters one, and how little of its life happens anywhere near where people can watch, and you have an animal that stayed a mystery, not because it was hiding, but because there was nothing on it left to read. The breakthrough came from a part of the body that almost never changes once it forms: the lens of the eye. The center of a shark's eye lens is laid down before it is even born, and this is the part that matters. Unlike many other tissues, the proteins right at that core are never replaced afterward. That tiny central knot of tissue simply stays as it was. It is, in effect, a frozen sample of the chemistry of the world from before the shark was even born, carried around inside its eye for its entire life. So researchers went after it with radiocarbon dating, the same method used to date ancient wood and bone. And they had an unusual stroke of luck built into the 20th century. Nuclear weapons testing in the 1950s and 60s released a pulse of radioactive carbon into the oceans a sharp, datable spike scientists call the bomb pulse. That spike acts like a timestamp in the water. If the core of a shark's eye lens carried that bomb carbon signature, the animal was young-born after the 50s. If the core was formed from older, pre-bomb carbon, the animal was old, much older. By reading the radiocarbon in the lens cores of 28 sharks and calibrating against that bomb pulse, the team could estimate when each animal was born. That is where the numbers came from. A maximum lifespan of at least 272 years for the species, and the largest single specimen estimated near 400, plus or minus roughly 120. Not a simple guess anymore, an age estimate, anchored to real radiocarbon measurements, with the honest error bars that come with any estimate like it. Sit with how strange that is. To find out how long this shark had been alive, scientists read a chemical fingerprint of the ocean, sealed inside the animal's eye on the day it was born, and matched it against the fallout of Cold War bomb tests. The animal carried the evidence of its own age in the one tissue it never renewed. That's how we know. And it's the same organ, the eye, that hands us the deepest surprise of all. Because, for a long time, everyone assumed that eye was a ruin. If you ever saw a Greenland shark up close, one detail would stop you. Its eyes usually look wrong. Clouded, pale, as if something had gone badly wrong with them. The reason is a small parasite, a copepod, that latches onto the surface of the eye and feeds there. It's called omatocoita, and it is remarkably common on these sharks. In some populations, the great majority of individuals carry it, dangling from the eye, clouding the cornea. Put that together with the fact that the animal lives in cold, near lightless water, and for decades scientists drew the obvious conclusion: this shark must be close to blind, and eyesight must barely matter to it. It was a reasonable assumption. It also appears to be wrong, because when researchers finally examined the eye itself in detail in a study published only recently, they found close to the opposite of a ruin. In the adult samples they studied, every major layer of the retina, the light-sensing layer at the back of the eye, was intact. And here is the part that stops you. In specimens estimated to be more than a century old, there were no obvious signs of age-related breakdown. A tissue that normally shows measurable deterioration with age, including in our own eyes, showed no clear degeneration in the samples they examined. The clouded corneas that made everyone assume blindness turned out to still allow substantial light through to that retina. The eye wasn't obviously breaking down. If anything, it looked actively maintained. And that retina is beautifully specialized for exactly where the shark lives, packed densely with rod cells, the kind tuned for the faintest possible light, with a light-sensitive pigment shifted toward the narrow band of blue that reaches the deep. This is not the eye of an animal that gave up on seeing. It's the eye of an animal built to see in almost no light at all and to hold on to that ability for well over a century, and possibly much longer. How does it manage that? The researchers found one intriguing clue. The retina shows robust expression of genes associated with DNA repair the cellular machinery that fixes the molecular damage that normally accumulates in an eye with age. That may help the retina hold itself together over such a long life. It's a candidate answer, not a closed case. But it points somewhere important. The eye isn't simply the cost of a long life. It may be one of the clearest windows into how this animal stays functional at all, and vision is only part of how it finds food. It also carries an extraordinary sense of smell, tiny pits that pick up the faint electrical fields of living animals, and a lateral line that feels water moving nearby. The organ everyone wrote off turns out to be one more piece of the same deep mystery. How does anything in this animal keep working for centuries? One quick aside, because it's the reason you should never eat one fresh. Its tissues hold high concentrations of urea and a compound called TMAO, which help keep its chemistry and proteins stable under the pressure and cold of the deep. But fresh Greenland shark flesh can cause serious intoxication, which is exactly why the traditional Icelandic dish is fermented and dried for months before anyone eats it. So the picture sharpens and gets stranger. A slow animal, with an eye built to outlast a century, thriving where almost nothing else its size can. But it still has to eat. And that leaves the one thing the simple version of this story never quite answers: what does a shark this slow actually manage to catch? For a long time, the easy assumption was that the Greenland shark is basically a scavenger, a slow vacuum of the deep, eating whatever dies and drifts down to it. And a lot of what turns up in its stomach fits that story perfectly. Researchers examining stomach contents have found fish and squid, and alongside them the remains of animals far larger than any shark could bring down alive, including large land animals that could only have entered the water already dead. That's scavenging, plain and clear. This animal is an opportunist, and it clearly takes carrion. But then there's the part that doesn't fit. Among the remains found inside these sharks are seals, and some of those remains are unusually fresh. Fresh in a specific way, some lacked the small scavenging creatures researchers would expect on a carcass that had been dead and sinking for a while. That doesn't prove a kill scavengers aren't a perfect clock, and how the shark is caught can affect what's found. But it is consistent with the seal having been eaten very soon after death, possibly after being taken alive. And that points somewhere the simple scavenger story can't follow. At least some of the time, this slow animal may be capturing living prey. Seals, perhaps, resting in the water in the dark, where a silent, slow-moving shark that hunts by dim light vision, smell, and the feel of moving water might be exactly the wrong thing to share the water with. Now the honest caveat, because this is where a lot of retellings overreach. No one has actually filmed a Greenland shark hunting and catching a live seal in the wild. The evidence supports the possibility that at least some prey is taken alive, but it does not reveal the method. How a shark this slow, moving at a walking pace, closes the final distance on a seal capable of moving many times faster is genuinely not understood. It's one of the real open questions about the animal, not a manufactured mystery, but a gap in what anyone has actually observed. So the portrait shifts. This is not a passive relic riding out the centuries. It is a slow, patient, sensory hunter that has been quietly good at staying alive and at finding food for longer than almost anything else with a backbone. Which makes the last twist the strangest of all. For all that toughness, the species is far more fragile than its size suggests. The cost of living this long is paid in one currency, time, and the animal pays it up front before it can ever reproduce. Consider how long it takes just to grow up. At less than a centimetre a year, reaching adult size takes a very long time, and the evidence suggests a female Greenland shark may need to be around 150 years old before she is even capable of reproducing. Read that again. This animal may spend roughly the first century and a half of its life not yet able to breed. There are human family lines that haven't lasted as long as one Greenland shark takes to reach maturity. Everything about it runs on that same stretched clock. It grows slowly and matures extraordinarily late, and other basic facts including how often a female actually reproduces remain poorly understood. And that has a consequence most people never think about when they hear 400-year-old shark. We tend to imagine that old means tough, that an animal this ancient must be nearly indestructible. The truth is closer to the opposite. An animal that may need a century and a half just to become capable of breeding is fragile in a very specific way. Remove the large breeding adults, and replacing them doesn't take a few years. It can take multiple human lifetimes if it happens at all. Which is exactly where this whole story finally lands. So how does a Greenland shark live for centuries in the dark? The age evidence itself is strong, even if the exact number stays broad, a maximum lifespan of at least 270 years, with the largest specimen estimated near 4 centuries, red out of radiocarbon sealed in the core of its eye. Cold water and an exceptionally low energy demand are probably part of why its life stretches so far, but the newer eye and genome research suggests they aren't the whole answer. Its biology appears unusually good at maintaining its tissues against the damage that ages most animals, though researchers don't yet know which mechanisms matter most. It survives the dark not with failing eyes, but with a specialized visual system that, in century-old specimens, showed no obvious sign of breaking down. And whether it truly hunts live seals, how a shark this slow catches anything fast in the dark, is a question the evidence raises, but has not yet answered. But here's the part the 400-year-old shark headline always leaves out. A lifespan that long is not a sign of strength. It's a sign of slowness, and slowness cuts both ways. An animal that may need a century and a half just to become capable of breeding cannot recover quickly from anything we do to it. The nets, the bycatch, and rapid climate-driven changes to its cold habitat and prey for a species that measures its recoveries in human lifetimes. Those are not small pressures. Some of the Greenland sharks alive right now may have begun their lives before the microscope was in common use, before most of modern science existed at all. They reached the present by growing slowly, maturing slowly, using remarkably little energy for an animal of their size, and simply outlasting the centuries in the cold and the dark. But the same strategy that carried them this far is the one thing they cannot speed up now that the pressures have changed. They survived 400 years by living slowly. Whether we leave them enough time to keep doing it is up to us. Next, we follow another survivor into that same darkness, because the ocean's strangest hunters are rarely the ones you'd expect, and the deep is full of them.